Um, Welcome everybody to this International Symposium of Mathematical Methods Applied to the Science. We start with the session of Geometry and Topology with Alfonso Zamora Sáenz, currently Assistant Professor at Universidad Politécnica de Madrid. He will talk about his work, the moduli stack of principal ρ-sheaves and Gieseker-Harder-Narasimhan filtrations. We start with you, Alfonso. Thanks.
Thank you, Jesus and Ronan, the organization of this nice symposium, for the opportunity to be here again, although virtually, but it's always a pleasure to be in Costa Rica again. So let me share the screen. So I guess now you can see the presentation, right?
Yes.
Okay. So the story I'm going to talk about today is, so the title is the moduli stack of principal ρ-sheaves and Gieseker-Harder-Narasimhan filtrations. So this is a joint work with Andrés Fernández Herrero from Cornell, USA, and Tomás Luis Gómez from ICMAT in Spain. And what we do is to study a problem, the problem of constructing a moduli space for principal bundles over higher dimensional varieties, but with a stack point of view. So with a point of view which is stack intrinsic. Using that theory from the stack, we're able to provide a new notion of a Harder-Narasimhan filtration, which is what we call a Gieseker-Harder-Narasimhan filtration that I will explain. So the outline, let me give you some preliminaries, and then I will talk about the problem of constructing the moduli stack of principal sheaves. Then I will talk about the filtrations, and maybe if I have time, I will try to give an example of a Gieseker-Harder-Narasimhan filtration. I apologize in advance because probably I put too much information in the slides for the time I have, but on the other hand, I can freely share the slides to anyone who could be interested in the subject. So the setup for this is K will be a field of characteristic 0. This doesn't work to the full extent in positive characteristics. So let us restrict ourselves to the characteristic 0. X is a smooth projective variety, which is geometrically connected of dimension D over the field K with a polarization. So O1 is an ample line bundle on X, which is a polarization. Then we use this notation for the fiber product over another scheme S, the notation X S. And for the group, so we're going to study G bundles. So we need a group. G will be a linear reductive algebraic group over K. And then ban G of X is the moduli stack of principal G bundles on X. The data of the group will be encoded in a representation. So ρ is a representation from G into GLV, where V is a K vector space of dimension R. And I remark that the representation has to be faithful. So G goes faithfully into GLV for the objects I'm going to consider. So the story of principal bundles and the story of the construction of principal bundles goes back to Ramanathan in 1975. Who over curves construct a projective moduli space of semi-stable principal G bundles using GIT, using geometric invariant theory, with what is understood as a stability condition of slope type or Mumford type or Mumford-Takemoto type. So it is a stability condition measuring the different degrees of certain line bundles. So measuring just a quantity, which is a number encoding data of the objects we want to classify. On higher dimensional varieties, so when the variety of X is greater than 1, there are several works of Gomez, Langer, Schmidt, and Sols in the first decade of the 2000s. They need to consider the generations of principal G bundles in order to construct a proper moduli space. So this is similar to when we have to consider torsion-free sheaves when considering the moduli space of vector bundles on higher dimensional varieties. And then they construct a moduli space using GIT, now with a stability condition which is of polynomial type, what is usually called a Gieseker type stability condition. So it is a stability condition measuring not just the degree of the objects, but a polynomial, the Hilbert polynomial, which encodes all the Chern classes of the objects we want to classify. So the first goal of the talk and of this work is to give a stack theoretic interpretation of this modular space over higher dimensional varieties, but avoiding GAT. When using GAT to construct these modular spaces, there are many technical details we need to check, which we can avoid from the stack theoretical point of view. So that's the first goal. For those not familiar with these stability conditions, let me give you a quick overview of what they are. So given a vector bundle E over a polarized variety, we denote by dig and rk the degree and the rank of the vector bundle. Then mu usually denotes the slope of a vector bundle, which is the quotient of the degree over the rank. So the rational number coming that way. Then we say that a vector bundle is a slope semi-stable if for every non-zero proper subbundle, the slope of the subbundle is less or equal than the slope of E. If the inequality is strict, we talk about stable objects, stable vector bundles, and otherwise, so if we are able to find a subbundle with a greater slope, then we say that E is slope unstable. Over higher dimensional varieties, what we do is to use, instead of the degrees, we use the full Hilbert polynomial. What is the Hilbert polynomial? It is the Euler characteristic of the torsion-free sheaf E twisted by n. So the twist is tensoring E by On. And then the Euler characteristic is the alternating sum of the dimensions of the cohomology groups, which turns out to be a polynomial in the Chern classes. So for example, the top degree, so the leading coefficient, except this denominator of the factorial, is the rank of the vector bundle, in this case, the rank of the torsion-free sheaf. We also denote by small p with a line, so a small overlined p, the reduced Hilbert polynomial, which is the Hilbert polynomial divided by the rank. Then the definition of Gieseker semi-stability is the analog with the Hilbert polynomial. So a torsion-free sheaf is Gieseker semi-stable if for every non-zero proper subsheaf, the reduced Hilbert polynomial is less or equal to the Hilbert polynomial of E. With the stability condition appears the notion of a Harder-Narasimhan filtration. So for unstable objects, we can construct in a canonical way a unique filtration, which is called the Harder-Narasimhan filtration, which in the slope case is a filtration verifying these two properties, verifying that the slopes of the quotients in this filtration, so the consecutive quotients between two consecutive terms, form a decreasing sequence of slopes. And then all quotients are slope semi-stable, so we cannot further stabilize the quotients. There's an analog for torsion-free sheaves using reduced Hilbert polynomials, which is encoded in this second definition. So a torsion-free sheaf has a unique canonical Gieseker-Harder-Narasimhan filtration, verifying the same condition, but for the reduced Hilbert polynomials. This is for vector bundles and torsion-free sheaves, and what happens for G bundles, for principal G bundles. So going back to Behrens' results, and then this was Hoya, they construct the analog for principal G bundles over a curve, which is a canonical reduction to a parabolic. So the point is that the notion of a filtration is encoded as a parabolic, as a reduction to a parabolic of the group G. And then this parabolic gives me a Levy quotient, being G over P is this L, this Levy quotient, and the semi-stability of the quotients now turns out to be the semi-stability of the associated principal L bundle under this quotient. Over higher dimensional varieties, there are results. There are this result by Anshush, Azad, and Biswas, and then Gurjar and Nitsur applying the result to stratifications in the moduli problem. They showed existence of these canonical reductions on higher dimensional varieties, but for slope stability conditions. So for certain stability condition, say measuring just the degree of certain objects, but not a polynomial stability measuring all the possible Chern classes appear in the objects we want to classify in the moduli problem. So given that there have been difficulties in attempting to introduce a notion of Harder-Narasimhan filtration with a polynomial or Gieseker stability condition for the problem of principal bundles, it is interesting to explore whether this notion can exist. And we show in this problem, in this paper, a new notion of Gieseker-Harder-Narasimhan filtration for principal sheaves. So that is the second goal of the talk. What is the stack approach of the problem? So it is the following idea. There are two results, two together similar results, one by myself together with Gomez and Sols, and the other one by Vicky Hoskins, showing that these Harder-Narasimhan filtrations can be thought from the GIT or from the moduli problem point of view as a Kempfness filtrations or Hesseling stratification filtrations. So using this Kempfness theory and the Hesseling stratification, you can recover the notion of the Harder-Narasimhan filtration from the GIT problem. But for those familiar with GIT constructions of moduli spaces, usually you embed the objects you want to classify into certain quad scheme, getting larger and larger with certain twists. So for different twists, you get different GIT problems. And for each GIT problem, you get a different quotient. And then although you recover the same moduli space, the filtrations or the stratifications in instability types or in Harder-Narasimhan types could be different. So this is why I write here that this GIT gives you natural stratifications on the stack, but not globally, but on some truncation of the stack. Then there is this nice theory by Halpern and Einstein coming from his PhD thesis, which is the theory of theta stability and theta stratifications, which are stratifications of the full stack by locally closed substacks. These stratifications are analogs to these Hesseling-Kempfness stratifications. But now the stratification is stack intrinsic, and it goes for the full stack, not just for some truncation of the stack. And this allows to show some notion of Harder-Narasimhan filtrations in the stack problem, but from the stack point of view, without going by the GIT theory when constructing a modular space. Another ingredient is this theory, this result by Jarrod Alper, introducing the notion of good modular space in an algebraic stack, which recovers the notion of Mumford for quotient stacks, and then putting everything together with Jochen Heinloth's expertise, they show an alternative stack theoretic approach to construct good modular space for Artin stacks, which is somehow generalizing Kiels-Morris result for the linked Mumford stacks. So this is a little bit of the stack approach. So let me define the problem. Let me define the objects we want to study. So for us, a principal ρ-sheaf will be a pair where F is a relative torsion-free sheaf of rank R over X. X is an S scheme. And then sigma is a section of the structure morphism of reductions. So a couple of observations. What means F being relative torsion-free? It means that there exists an open big, big is being of codimension greater or equal than 2, open set where F is locally free. And then the scheme of G reductions, using the work of Schmidt, the sections of this morphism are in bijection with G reductions of the structure group, agreeing with the restriction of F over U. So this is where you recover the action of the group in this section of this morphism. Then this defines a stack. So this defines a pseudo functor from affine schemes into groupoids, which is the groupoid of so for each scheme, S is the groupoid of ρ-sheaves over XS. These are the objects. Then how to study this stack and how to provide a stratification of this stack in, say, different Harder-Narasimhan types or different stability type, with the notion of theta filtration, which is the stack analog of one parameter subgroups. If you remember what one parameter subgroups in a GIT construction, then a one parameter subgroup is measuring through the Hilbert-Mumford criterion, is measuring whether a point is GIT stable or unstable. So this will play the same game in the stack. So let them be a stack over K, and then capital K is a field extension, and P is a capital K point. Theta K is this test stack. This test stack, which is the affine line over K over the multiplicative group, where the action of this multiplicative group assigns weight -1 to the variable T. This has a close point, which is 0, and 1, which is an open point. Then a theta filtration of a point P is a morphism of stacks, where the image of 1 is isomorphic to the point P. And then we recover the different weights of this action on the stack M in the graded point. So the restriction of F to the graded to the point 0 is what is called the associated gradient of the filtration. This definition is very abstract, so trying to make it a bit more concrete, if M is something a bit more familiar as it is the stack of torsion-free coherent sheaves over a variety, then a theta filtration of a sheaf is equivalent by something which is called the risk construction, is equivalent to a Z filtration, so a filtration indexed by the integers, which is a filtration where just a finite number of terms are different. So there are an infinite number of zeros on the left and an infinite number of terms equal to the original F on the right. All the quotients are torsion-free sheaf, and then we have this associated gradient, which is this direct sum of these quotients. Note that in this graded object, just a finite number of pieces are non-trivial, are different from zero. What is the notion of theta filtration in the stack of principal bundles? So in the stack of principal ρ-sheaves, a theta filtration of a point F, of a point F sigma is a pair, where the first element of the pair is a theta filtration of the underlying torsion-free sheaf. And then P, what is P? So there is a maximal big open set where the associated gradient is locally free. And then on that U cross the stack, P is a G bundle. P is a G bundle such that the push forward for the representation by the representation rho is an associated GLV bundle. So if we use the representation of the group G into GLV, then we get a GLV bundle, which agrees with the restriction of this filtration to the open set U. So this is how we relate the filtration of the underlying torsion-free sheaf with the action of the group in the object. Then we can define another groupoid of this theta filtration, which is equivalent to the groupoid of pairs of filtration together with this object P, which is somehow the reduction of the group G. Let me skip most of this slide just to say the following. In the split case, this can be done even more concrete. Because if G is not split, then we cannot use the theory of parabolics and Levy subgroups when trying to make these filtrations more concrete. But if the group is split, then we can also use co-characters of the group, defining parabolics, and then this P restricted to the one of the stack gives me another bundle, which is G, and then G lambda, which is a reduction of G to the parabolic subgroup. Then we can make this filtration into a sequences of reductions to parabolics and Levy subgroups, which allows to play a wonderful game at the end. But for that, we need the group to be split. If it is not split, then this full description is quite obscure, not really concrete. Once we have in the GIT problem a one parameter subgroup, then to apply the Hilbert-Markov criterion, we need some weight, some numerical criterion to determine whether a point is GIT stable or GIT unstable. In the stack, we have what is called a numerical invariant, and in this particular case, for this stability condition, it is a polynomial numerical invariant, which is a function taking one of these theta filtrations and assigning a fraction where the numerator is the weight of certain line bundle constructed in the stack. The definition is a bit involved, so I also skip it. And the denominator is a norm on certain cohomology group. This is a polynomial because the weight turns out to be a polynomial. Using this result of Halpern, Neistat, Herrero, and Jones, they do this construction for the stack of torsion-free coherent sheaves. And they show that this weight can be written down as this sum involving the reduced Hilbert polynomials of the pieces in the filtration. And then the denominator is a number encoding the ranks of the quotients of the filtration. This defines a notion of stability because we can play the same game as in geometric invariant theory and say that and show that if a ρ-sheaf, if an object is Gieseker semi-stable, then this is equivalent that for every filtration, this numerator is non-positive. And the other way around, if we can find a filtration for which the value of the numerator is negative, then that's as a destabilizer. That object is unstable, and we can find a way of destabilizing that object. So this is a generalization of the Hilbert-Marford criterion in this case. What is all of this for? For this theorem of Halpern-Leinstein. So once we have a numerical invariant on a stack, in general, satisfying a series of properties, let me go over them. This has to satisfy two properties called theta and S monotonicity. These two properties are filling and extending properties. So this numerical invariant needs to behave well with respect to filling gaps and extending objects in the moduli stack. The second property is called HN boundedness, and this is the following. Whenever I have an object which is unstable, is because there exists a way of destabilizing that object. But there could be different ways of destabilizing an object. It happens that for every stabilizing filtration, given a positive value of this numerical invariant, we can find a more destabilizing one, so giving even greater value, but in a fixed bounded family. So this means that in order to get the best destabilizers or get the candidates to be a Harder-Narasimhan filtration, we can find them in a finite dimensional place, in a bounded family. So that's the point. Then we also need to show that the semi-stable part is bounded. And then we also need to show the existent part of the evaluation criterion for properness. If the first three properties hold, then the numerical invariant induces a theta certification on the stack, and the semi-stable locus admits a separated good moduli space, good in the sense of this Alper's theory. If 4 holds, then this moduli space is proper. Then, for example, this theorem in our case, in the case of the principal ρ-sheaves, when G is semi-simple and ρ is the adjoint representation, this recovers a construction already done in the literature, which is a construction of Schmidt, Gomez-Solz, and Gomez-Langer, Schmidt, and Solz, but providing an alternative approach, which is intrinsic to the stack. Also, for other cases not really contained in the previous literature, this allows moduli spaces for different principal ρ-sheaves with different representations of the group G. Let me say some words about the monotonicity property, because this monotonicity property means the following, and is really the technical key part of this story. To prove monotonicity, we need to generalize this result, and the idea is to generalize Atiyah-Bot's symplectic reduction and Donaldson infinite dimensional symplectic reduction in gauge theory, but in an algebraic way. So this is doing the algebraic counterpart of this symplectic reduction by these authors. This is done through some object which is called an affine Grassmannian of higher dimension, and these parameterized objects in somehow an infinite dimensional GAT. So instead of having a finite dimensional problem of GAT where we have a quote scheme which embeds into a finite dimensional projective variety, and then in that projective variety we perform GAT, then we perform somehow an infinite dimensional GAT process to the full, to all the quote schemes at the same time, somehow. The role played by the gauge transformations in Atiyah-Bot's and Donaldson reduction, now it's played by some infinite dimensional algebraic group of rational gauge transformations. So this is the idea of what monotonicity means. Then the first theorem of this work says that all these conditions hold, then we can apply this theory. So being new the polynomial numerical invariant I defined before, this polynomial numerical invariant is both strictly theta monotone and S monotone, and it satisfies the HM boundedness criterion. Then it defines a theta certification on the stack. We also show that the substack of the semi-stable objects satisfies the existent part of the evaluative criterion for properness. And also, if we fix the degree and the Hilbert polynomial, so if we fix the numerical invariant, the substack of semi-stables is quasi-compact, so it's bounded. Then it admits a proper good moduli space, which is also separated if ρ is central. So if ρ takes the center of G to the center of GLB. And talking about the center, we can extend this setting to even more general representations, representations going from G to a product of GLVs, of general linear groups, to get the following. So to allow these reductive groups G to have large center, because the center of GLV is one-dimensional, then given that the representation needs to be faithful, if we allow this target to be a product of general linear groups, then we allow groups G with larger center to play in this story, and then we can get this theorem in much more generality. Now let me say some words about what is a Gieseker-Harder-Narasimhan filtration and how to construct it. If we have an unstable object, then it is because there exists at least one filtration giving a positive quantity for this numerical invariant. Then let us define these A's being the suprema of the values of the numerical invariant for each unstable object F sigma. So the supremum taken over all possible filtrations giving positive quantity in this numerical invariant. Then this stratification, the theta stratification is indexed by certain polynomials, where each strata can be described as all the objects whose supremum is bounded by this polynomial. So as an observation to get some sense of this definition, for the semi-stable ones, so for the lower strata, the M0, then this supremum is 0, because all the filtrations give me a numerical invariant which is less or equal than 0. Then it can be shown that the supremum of this is 0. Then this is the lower part. But over it, we have many different types of unstable objects which form the stratification in the stack. Then we show that any object has a unique filtration. We call it a canonical theta filtration, which can be thought as a leading term Harder-Narasimhan filtration. The name leading term will be a bit clearer in the next slide. What does it do, this filtration? So it gets that this filtration achieves the supremum in this definition. Sorry. This is equivalent to giving a canonical filtration of the underlying sheaf, and in the split case, this filtration also comes from some weighted parabolic reduction. So we can also play some game with the parabolics and the Levi subgroups. Let me say something about why the name leading term filtration, which explains most of the ideas behind this filtration. Suppose that G is GLV already, and the representation is the identity. Then one of these principal ρ-sheaves is indeed a torsion-free sheaf, because the group is GLV. Then this is equivalent to a torsion-free sheaf. Consider the Gieseker-Harder-Narasimhan filtration of F. So what is this Harder-Narasimhan filtration? It is a filtration for which the sequence of reduced Hilbert polynomials of the quotients gives me this chain of inequalities. These are inequalities between polynomials. So this means that at each gap, this strict inequality means that the inequality between the polynomials can occur at some degree of the polynomial. It could happen that it occurs at the degree d-1. I recall that the top degree, the degree d of the dimension of the variety, is the same for all of them, because all of them are reduced Hilbert polynomials. So the top degree is the same for all the polynomials, but the first possible differences can appear at the degree d-1, d-2, up to 0. But the degree at which the difference occurs for each inequality could be different. Then we define I to be the leading index, and then mu I the leading slope, when the leading slope is the slope of that degree coefficient over the rank. It is like an intermediate slope. Instead of the degree, the actual degree of the sheaf over the rank, the combination of Chern classes at some degree of the polynomial over the rank. We choose that degree to be the highest possible, such that this sequence of slopes, at least we find one inequality. So this means that if the original object is slope unstable, then it is sure that we can find at least one inequality at the highest possible slope. But if it is not a slope semi-stable, but it is Gieseker semi-stable, so we can find some destabilizer, but using the Hilbert polynomials, then we need actually in the filtration to be differences at lower terms of the polynomial. Let I be the highest possible index, and that is the leading slope. Then what is the leading term filtration with our definition? It is precisely the filtration extracting from this Harder-Narasimhan filtration just the terms where these gaps appear at this index. So we extract, say, a subfiltration, getting just those terms where these differences at that slope appear. I write here that if f is slope unstable, then the leading slope is really the maximal possible slope, which is d minus 1, this index, this maximal index, and this leading slope is mu. So how do we construct what we call the Gieseker-Harder-Narasimhan filtration, iterating this process? So I'll go a bit fast over this, but the story is, we first get this leading term filtration. This leading term filtration gives me how to get those elements of the Gieseker-Harder-Narasimhan filtration at the top degree where we find the differences between the Hilbert polynomials. This provides some weighted parabolic reduction, and then some Levy subgroup, and provides a graded object. Take the graded. If the graded is semi-stable, we stop. But if it is unstable, then we can take a second leading term filtration for this graded object. And then all the quotients appear which are not semi-stable, which are Gieseker unstable. We apply again to these pieces of the graded object, this iteration of the leading term filtration, and we refine the filtration until the end. This process stops because of the dimensionality of the polynomials and the varieties, and we arrive to a unique filtration. So the second main result is that this process provides a unique filtration defined recursively, which we call the Gieseker-Harder-Narasimhan filtration, because it is constructed recursively with a polynomial stability condition. This Gieseker-Harder-Narasimhan filtration does not have to share wonderful properties in comparison with the classical Harder-Narasimhan filtration, but in the split case, we get this really important property that the associated Levy sheaf is Gieseker semi-stable, which is something desirable in this theory. Of course, for torsion-free sheaves, this Gieseker-Harder-Narasimhan filtration coincides with the classical one, as one could expect, right? I guess I'm running out of time, so let me give a quick glimpse of an example. It is not so easy to construct examples of Gieseker-Harder-Narasimhan filtrations, but let me say the following. For a special orthogonal bundle of dimension 7, which is this F, where we have 4 copies of the structure sheaf, and then 3 ideals, where L is a line in P3, Z is 2 points, and P is one of these 2 points. Then we can construct, we can give a symmetric bilinear form, and we can give a structure of a SO7 bundle, which happens to be a slope semi-stable. Then following Ramanathan's definition and Anshusa's that this was definition of canonical reduction, the canonical reduction is trivial. So we just we can expect to have a notion of Gieseker-Harder-Narasimhan reduction, but using Hilbert polynomials, not using just the slope, because at the slope level, the canonical reduction is trivial. And this process allows, so this theorem allows to construct a Gieseker-Harder-Narasimhan filtration for this SO7 bundle, because if you look at the Hilbert polynomials, then you find that the first term is the same for all of them, because all of them are rank 1 pieces. The second term, so the degree 3 minus 1, 2, the degree d minus 1 term is the same for all of them. This is why this is a slope semi-stable, because we cannot find differences at the level of the degree 2 coefficient. But at the level of degree 1 coefficient, we can find differences, and at the level of degree 0, we can find differences. Then we will find differences at 2 levels of the Hilbert polynomial. This is why we will need to apply the leading term filtration twice to get this recursion until the Gieseker-Harder-Narasimhan filtration. Let me just say that the first iteration provides F, this rank 5 piece and this rank 1 piece. This rank, 7, 6, sorry, I said 5. 7, this piece is rank 6, and this is rank 1. The 6 and rank 1 pieces are orthogonal one to the other, because we not only need to look for filtrations of the torsion-free sheaf, we need to look for filtrations respecting the structure of an SO7 bundle. So we need to look for orthogonal filtrations and filtrations behaving well with respect to the bilinear symmetric product. If we look at this central piece, so if we look to the graded object of this, we find this IL, these 5 line bundles, this degree 1 piece, which is an SO5 bundle, and this rank 1 piece. Let me go back for a second to these Hilbert polynomials. The Hilbert polynomial of IL has the lowest and the different Chern class at this degree 1 of the polynomial. This is why it goes separated from the rest in this splitting of the graded object. And then this SO7, this SO5 bundle comprises these terms having the same 10n as this coefficient. Then applying a second iteration, we get that this rank 5 splits into 5 line bundles, and splitting into 5 line bundles mean that we cannot go any further, and this is the solution of the final Gieseker-Harder-Narasimhan filtration. So we start with this F, we have this O as the first iteration, but then for the central piece, we need a second iteration, reducing these differences in the Hilbert polynomial until we are done and it is no longer possible. And this is the notion of a Gieseker-Harder-Narasimhan filtration obtained at the second iteration. So let me stop here. These are some references. This one is the preprint of the work I talked today in this talk, and the others are the main references for this work. So thank you for your attention. Thank you very much.
Thanks, Alfonso.
So I have a question, if you...
Yes.
Go ahead, Marcus.
Thanks, Alfonso, for the nice presentation. I'm new to this Halpern-Leitner theory, and I hope you don't mind if I ask you a couple of things. So if you go back to the slide where you put the theorem by Halpern and Leitner. Yes, you mentioned a numerical invariant. What is it? What do you mean by a numerical invariant nu?
Yeah, so so this numerical invariant resembles a certain weight of a line bundle in a linearization of an action in the GIT setting, right? So it's some stack theoretic analog of that weight.
So it's like a choice of a stability condition.
Exactly.
Okay.
But in the fashion of the weight of a line bundle on the stack.
The weight of a line bundle on the stack. So and that somehow becomes the Hilbert polynomial, or the normalized Hilbert polynomial. Just like in the usual GIT theory, that GIT stability becomes the Gieseker stability, right? So it's...
Yes.
Okay.
So usually you show that that the Hilbert polynomial and the polarization you are using agrees with the choice of linearization in the GIT problem, right? So
yes.
So this is more or less a stack generalization of this fact.
Okay.
But the problem is that the definition of the line bundle on the stack is much more difficult. It's a bit of an ad hoc definition in the stack to, as you say, to agree with the stability condition you classically use, right? Because you want that notion of stability coming from the stack to agree with your usual stability on the objects you classically impose. In order to construct a moduli space, you know what moduli space is, right? So you know what kind of objects that moduli space is classifying.
Mm-hmm. Okay. Now, the other thing that perhaps you could say a few words is, what do you mean by a good moduli space in the sense of Alper? I guess it's a very technical thing, but maybe just a couple of words.
Yeah, it could be. It is not. I have to confess, it's not something I really completely understand because it is really deep in the stack. So it's a categorical property for these two functors in the stack, but I don't think I can say quickly a couple of words making sense. So the word good is good in the sense of good categorical properties from stack theory. So the moduli space you get is the one you want to get, and it does not contain more objects you need or less objects than the ones you need. But it is a very technical and categorical definition, not really something very geometrical. You can
some analog to stacks of the various concepts of moduli space in GIT, like you have a categorical quotient, a good quotient.
Yeah, that's it. So something. This is important in the stack theory because I said in one of the slides, so we have this kill-Morris result for the link man for stacks, but for Artin stacks and quotient stacks, kill-Morris does not apply to the full extent. So these new notions apply to stacks in the sense of Artin and quotient stacks, which are not necessarily the link man for stacks. So this extends the nice properties of kill-Morris result, these good categorical properties to these other kind of stacks with this theorem. So it allows more kind of quotients in the stack theory to give a geometrical meaning to the algebraic space, which is a quotient in these cases. But I'm sorry, I cannot say something really more geometrical.
Oh yeah, it's all very scary.
Yeah, it is.
Maybe my last question, so that I can understand. So in the Hoybrush and Len classical book, there is this. They have some intermediate notions of Gieseker stability as well, interpolating between mu stability and Gieseker stability. It's you consider the Hilbert polynomial, but then you truncate the Hilbert polynomial, ignoring lower, things of lower order in the Hilbert polynomial.
Yes.
Is this something analog that you're doing here?
This is let's say something which is on the list of checking list for us in the near future. So this this should have like a very good analog, but I have to say the analog should get easier in the torsion-free coherent sheaves case. When dealing with principal bundles, things can get very messy because principal sheaves is a sheaf together with a notion of group structure, and then the possible filtrations need to respect this group structure. Then in one of the easiest cases, the orthogonal case or the special orthogonal, filtrations are orthogonal, so are kind of balanced between with respect to the middle of the filtration. But for other groups, it can get really crazy. But for the case of torsion-free sheaves, probably what happens is that this notion of Hoybrush and Len of intermediate stability is where is it? So this filtration, this leading term filtration, getting just the terms of the full Harder-Narasimhan filtration of the slope I want, should be really the filtration you get if you restrict to the notion of stability, notion of, say, truncated stability or truncated Gieseker stability. So I'm pretty sure it is the same. But this is something it should be carefully checked. But thanks for the comment. Yeah.
So
thank you very much, Alfonso.
Thanks, Alfonso. Yeah.